Dear students, in today's class, let's begin with the concept of indices. Let's learn the concept of indices. To explain this concept, I'll take few examples. Let me take the first example as 2 into 2 into 2 into 2. What we can observe here is the repetition of the digit 2 with respect to the multiplication, and the digit 2 is repeating 4 times. Now this repetition I can also write as, now the digit 2 is repeating, so I'll write 2 as it is, and it is repeating 4 times, so I can write it as 2 raised to the number of times it is repeating, so 2 raised to 4. I'll take another example, say 6 into 6 into 6. In this example, the digit 6 is repeating, and it is repeating 3 times. So I can write it as 6, and it is, since it is repeating 3 times, I can write it as 6 raised to 3. One more example if I can give, 7 into 7 into 7 into 7 into 7 into 7. Here I can observe the digit 7 is repeating, and it is repeating 6 times. So I can write it as 7 repeating 6 times. So 7 raised to number of times it is repeating, that is 6. So writing these repetition in terms of the number raised to the repetition, number of times it is repeating, this concept we call as the concept of indices. Now in this concept we are using two important words. One is the base, another one is index. Now the base is nothing but the digit which is repeating. In the first case, the digit which is repeating is 2, so we call 2 as the base. In the second case, 6 is the digit repeating, so we call 6 as the base. In the third case, 7 is the digit repeating, so we call 7 as the base. Now, the number of times it is repeating, that digit we call it as index or the exponent. Over here, the digit is repeating 4 times, so this 4 we call it as index or the exponent. Here, the digit is repeating 3 times, so we call this 3 as index or the exponent. Here, the digit is repeating 6 times, so we call this 6 as the index or the exponent. So these are the two important words we need to remember in this concept. Now, keeping this introduction in mind, let me give you the general terms with respect to indices. So, in general, if A is any real number and n is a non-zero positive integer, that means A is base, and A can be any real number, means there is no restriction to A. A can be a positive number, can be a negative number, can be zero, can be in terms of fraction, etc. So for base there is no condition, and n is a non-zero positive integer where n is a power and we have a restriction for n, that is n can only be a positive integer. So in such case, if I have the product of A, that is the repetition of A n times, if the base A is repeating n times, then I can write A as, since it is repeating n times, n raised to n, A raised to n, where we call A as the base and n as the power or the index or the exponent. Okay, this is in general. Now let's look at the certain laws under indices. We have the first law. that says a to the power m into a to the power n is equal to a to the power m plus n. Means if we have the repetition of the same base with respect to the multiplication, then we can write the base only once, but the powers we can add. If we have the repetition of the base, then we can write the base only once, but the powers we can add. For example, if I have 2 to the power 3 into 2 to the power 2. Now the base is 2 and it is repeating 2 times. What we can do is we can write it only once, but the powers we can add. So if I add the powers 3 and 2, I will get it as 2 to the power 5. If I take another example, 6 to the power 1 into 6 to the power 2 into 6 to the power 3. The base is common here, which is 6, so I can write it only once. And the powers I can add. So if I add the powers, what I'm going to get is 6 to the power 6. So this is the first law, which says if we have the repetition of the base with respect to the multiplication, we can always add the powers. Let's look at the next law. The next law is also same. A to the power n divided by a to the power n is equal to a to the power m minus n. Means if we have the repetition of the base with respect to the division, we can write this as only once, the base only once, whereas the powers will be numerator power minus the denominator power. For example, if I have 2 to the power 3 divided by 2 to the power 2, I can write this as 2 to the power 3, that is the numerator power, minus the denominator power, that would be 2 to the power 1. Another example if I have 7 to the power 3 divided by 7 to the power 5, now 7 is the base repeating, I can write it only once and the power can be the numerator power minus the denominator power, which will give us 7 to the power minus 2. But what we can observe here is we have the negative power, which is not possible. Since the negative power is not possible according to the definition of indices, so we need to convert it in terms of a positive power. So to convert in terms of a positive power, we have immediate next law. That is, the next law says if you have a to the power minus n, we can always take the reciprocal of the base. The base is a here, you can take the reciprocal of the base, whereas the power will remain with a itself, but the power will change the sign. For example, what we have in the previous example is 7 to the power minus 2. In order to make the power positive, I need to take the reciprocal of the base. So it will become 1 by 7. Now the power will remain with the 7 itself, but it will become positive. So we get the power as a positive power. Let's look at the next law. The next law says a to the power m to the whole power n is equal to a to the power m into n. Means we have single base but different powers. So whenever we have a single base, the base will remain as it is, the powers will get multiplied. For example, if I have 2 to the power 3 to the whole power 2, the base will remain as it is. I just need to multiply these two powers. So 3 into 2 becomes 6. If I have 6 to the power 1 to the power 3, 6 will remain the same. The power we need to multiply. So 3 into 1 becomes 3. This is it. Let's look at the next law. We have few note here. The first note says a to the power 0 is equal to 1. Means if our power is 0, if the power is 0, irrespective of the base, then the value will always be equal to 1. For example, 5 to the power 0 is 1. Power is 0, so the value is 1. 1 by 2 to the whole power 0, the power is 0, value is 1. Minus 100 to the power 0, the power is 0, so the value is 1. So this is the first note. Whenever we have the power as 0, the value is always 1. Let's look at the next note. The next note says qth root of a to the power p is equal to a to the power p by q. P will remain in the same position whereas qth root will go in its denominator. Before I give some examples under this law, let us look at the concept of root. Whenever I have square root of a, I can always write it as a to the power 1 by 2. Whenever I have cube root of a, I can always write in terms of a to the power 1 by 3. Whenever I have fourth root of a, I can always write it as a to the power 1 by 4. So the root terms we can always write in terms of power, and it is always 1 divided by the respective root. So similarly here also, if I take some example, cube root of 2 to the power 5 as the example, if I take 2 to the power 5 will remain same, whereas cube root I can write it as to the power 1 by 3. These are few note and some laws under indices. Using this, let's solve the problems. Let me move to the exercise. Exercise 3.1. Simplify the following. We have the first problem. 9 by 4 to the power minus 3 by 2. What I can observe here is the negative power. So my work is to make the power positive. And the law says if the power is negative, we have to take the reciprocal of the base. So 9 by 4 is the base. Take its reciprocal, which is 4 by 9. 9 by 4 is the base. Take its reciprocal, it is 4 by 9. Whereas the power will remain in the same place, which is 3 by 2. Now this I can also write it as 4 by 9 as it is, whereas the power 3 by 2, the denominator power, I can express in terms of root. It is square root. So to the whole power 3 will remain same. Now square root of 4 is 2 and square root of 9 is 3. Its whole power 3. 2 to the power 3 we will get it as 8 and 3 to the power 3 we will get it as 27. This is the required answer. Let's look at the next problem. We have the next problem. Cube root of x square, its whole power 3, its whole power 1 by 2. So we have two brackets over here. First look at the innermost term. We have x square, that let it be as it is. The next immediate term what we have is cube root. So cube root I can write it as 1 by 3. So into 1 by 3. After the cube root, what I have is the power 3. So that I can write it as into 3. After the power 3, what I have is the power 1 by 2. So I can write it as into 1 by 2. Now this 2 and 2 cancels, 3 and 3 cancels. All the terms in the power get cancels with respect to the multiplication and the division. So remains is 1. So anything to the power 1 is the value, the base as it is, which is x to the power 0. We have the next problem, a to the power x plus y into a to the power 2x minus y. What we can observe in this problem is the repetition of the base a. Whenever the base is repeating, we can write it only once. So I'm writing the base a only once, and here the base is repeating with respect to the multiplication. In this case, we can add the powers. So x plus y as it is, and 2x minus y, we can add it. So they will retain its sign. So what we get in the next step is a to the power x plus 2x will become 3x, and plus y and minus y will cancel. So this is the required answer. Let me look at the next problem. A to the power 2m plus n into a to the power 3m plus n divided by a to the power 4m plus n. We can observe the repetition of the powers in the numerator as well as in the denominator. Let me simplify the numerator part first. So the numerator base a, whereas the powers are 2m plus n and 3m plus n. So it is the multiplication of the same base, so I can add the powers. Whereas the denominator, let me keep as it is. Now if I simplify my numerator, I will get it as a to the power 5m plus 2n, whereas my denominator a to the power 4m plus 2n, let me write as it is, which is nothing but now once again repetition of the same base. So let me write it only once, but we have the numerator and the denominator. So the powers will be numerator power minus the denominator power. So I get this way. Now 5m minus 4m will give me a to the power m, whereas plus 2n and minus 2n cancels. This is the required answer. Let's look at the next problem. We have the next problem. 5 to the power 5 its power 0 plus 5 to the power 2 its whole power 0. Now, the moment we have the power 0, our work is to concentrate on that power and its base. So, if I look at the first very term, the power 0 is here and its base is 5. So, we need to simplify this first. So, that means this 5 will remain same, whereas 5 to the power 0 will become 1. Plus, if I concentrate on the next term, the power 0 is here and its base is 5 square. 5 square, this entire term is the base of 0. So, its power 0, so the value becomes 1. So, 5 plus 1 gives us 6. And this is the answer. Let's look at the next problem. 3 to the power 0, its whole power 3, plus 3 to the power 2, its whole power 0, divided by 3 to the power 2 its whole power 2 plus 3 to the power 3 its power 0. Once again, this is a problem with the power 0. So what we need to do is we need to concentrate on a term which has the power 0. The first term, if I see here 3 to the power 0, so power 0 is for this 3, so this is the base, so the value of this entire term becomes 1, whereas to the whole power 3 will remain the same, plus next term if I concentrate, the power 0 is here and the base is 3 square, so the value of this entire term will become 1, divided by 3 to the power 2 into 2 becomes 4, plus 3 to 3, its power 3 to the power 0. So these two terms I need to concentrate first. That means the base 3 will remain same and its power 1. So 1 cube is 1 plus 1, so gives us 2, divided by 3 to the power 4, which is 81 plus 3. That is nothing but 2 divided by 84. That is nothing but 1 divided by 42. This is the required answer.